So today we're going to looking at digital theater structure. Um, last couple of weeks, we have been doing some practical exercise using digital theater. So we filter noise signal and we shape the noise signal. We also did a signal restoration. So we have a piece of audio mixed with noise signal. We design and apply a filter to remove those noise. So I think you had some intuitive understanding and feeling about the digital theater. So today I'm going to go through some internal structure or some sort of a theoretical background about digital theater. It is one of the, I think, three most important aspects of the DSP for audio processing. I normally name these three aspects are convolution. Convolution is, well, actually, convolution is one type of the filter. I mean, but I single it out because it's important to reflect some natural acoustical property. Like you clap hand in the room, you have some reverberation, and you can use that as audio effects in digital way. Okay, convolution. Second is Fourier transform. By all means, is very important. That's the only effective way to estimate the spectrum of any signal. Third one, then it is digital theater. It is vast, big subject. The very popular audio music applications such as EQ or cross filter, whatever, low pass, high pass you use every day in your music making process are linked with filter. And most people do this in nowadays in DAW. So that's digital theater is very important. If you go to library to find any DSP book, I mean, it will be overwhelming, mathematical heavy, all right, in terms of digital theater. The way I teach digital theater is to minimize some theoretical burden, because our group is more focused on practical aspects. So as long as the engineering approach and the programming approach can be achieved, so we want to minimize some complex mathematical theory. But by all means, if you want to explore in more depth, that's welcome as well. Okay, I will put those towards the end, some of lecture slides and additional mathematical background of that. Okay, so let's go to the concept. So we actually done digital theater already. I mean, in specific aspect, which is FIR theater. The first slide, the picture shows here, everybody familiar, is this is basically a process of convolution. We have, on the left side, we have a delta function, and we input into a linear system, and we got impulse response. Actually, this impulse response can be used as a filter, and this filter is actually a FIR, infinite impulse response. The concept here is why it is called finite impulse response is because your input is just one pulse, and the energy we're going to die out. So the linear system is not going to have extra energy. There's no extra energy from outside. So this is closed system. So the energy going to die out for a finite, no matter how long, for finite time period of time, the energy going to die out. So the impulse response will going to become zero at some point. So it's a finite impulse response. We can then use this impulse response as a filter. So that kind of filter can be implemented in convolution. There are other ways to implement, but the most simplest way is, or intuitive way, is using convolution. So we then can use this impulse response, HN, as a filter kernel or FIR filter kernel. I mean, in digital filter domain, there are quite lots of different terminologies. They are inter-exchangeable. All right, don't be confused by those terminologies. So normally people talk about FIR filter kernel also refers to the coefficients of FIR filter. So in the later slides, we will say what are the coefficients. Okay, so this approach can implement, for example, a low-pass filter. Again, this diagram has showed before. That's this diagram showing the signal mixed with more than one frequency of components and apply a low-pass filter kernel in a convolution way and end up with just one signal component. All right, so left side there's signal with, left side I have signal which is like this zigzag, which is slightly high frequency components. And also I have a slow changing slope, which representing kind of a slow changing signal. Fast changing, high frequency, slow changing, low frequency. So this is my filter. This in the middle bit is my filter kernel. Yeah, we call it filter kernel. Those filter kernel are a bunch of number. Each number has certain value, and those bunch of number also is a coefficient of the filter equation, which we filter expression we're going to look at in a minute. So after apply a filter using convolution, so this operation is convolution, is not multiplication. Convolution is slightly more complicated. It's basically combination of adding different terms and multiply this together. And then the result will be a filtered signal which only left the slow changing slope, and all this zigzag, the zigzag signal is being eliminated because this is a low pass filtering process. The high frequency has been filtered out. So that's simple demonstration. So let's establish a proper mathematical representation of that, because in previous labs we have been giving out some been giving out some equations, but those equations seems hard to understand. So let's start from basics, how we're going to understand those equations. Couple of these slides are come from a very old website. I think it's done by a UK engineer, talk about the digital filter. Unfortunately, the website is no longer available. I think it's very, very good. So maybe I'm going to put something on the website in the future. So it's very less complicated and easy to understand. So I have to pay credit to this website. It's anonymous. I don't know who made engineer made a digital filter website. So some of my slides the idea come from there. Okay, so first of all, let's looking at the expression of any signal. Okay, so the first equation is analog signal. Okay, so using, that's why it's using V represent the voltage. So normally, I mean, in terms of audio signal, normally the sound going to be represent as a voltage in the system, right? So it can drive the speaker, or drive the microphone, etc. So it's a function of time, all right? So the xt could be a sine wave, could be any kind of arbitrary. So we're using parenthesis bracket, this bracket parenthesis, to actually representing analog signal, continuous analog signal. All right. So then the second equation demonstrates a sampling process. So this equation saying the xi with index I means x1, x2, x3, a discrete, a series of values. So those values are basically a snapshot of the original signal function. So in terms of replace the continuous time t with an index number I multiplied by a sampling period. So basically every 22 microsecond or whatever, depends on sampling frequency, you take the value. So eventually, the data will become bunch of numbers. Okay, I think we probably all not familiar with this process, and it is important for everybody to be able to visualize this process. Just imagine a continuous waveform has been taken snapshot, but this gives us some accurate expression in mathematical form. So then we end up with xn, a bunch of numbers. That's when going to, that is then the point we are doing MATLAB stuff, all this bunch of numbers. Okay, so in real world, this bunch of numbers going to be available, stored in the memory, and available for the DSP processor of computer. So then we ignore the middle bit. So at the end of the point, so at end of the system, not the end of system, then this component, this number is going to be manipulated by some algorithm, and then output algorithm generate another bunch of numbers. In that case, a discrete number again. So we normally name it y0, y1, y2, and so on. So then that value going to be sent into your a DSA device, and your DSA means digital to analog conversion. So you can convert to analog. And for audio processing, normally it goes to a speaker. All right. So the sound has been generated. So your filter signal is being generated. In general, the way how the y is calculated from axis, so there's a number of y's and number of x, is determines the filter action of digital filter, so filtering action. So what we're trying to establish is the relationship between y and x in the mathematical formula, and that also representing a digital filter. Okay, so then we can establish some simple. So we can start with very simple filter which human can understand very well. Then we can move to some complicated scenario. Okay, so first of all, this diagram showing a simple FIR filter. Well, we talk about a different type of filter later. Where so far we're all using FIR filter as example. So this is a very, very simple filter called moving average filter. It's actually very useful. I think last day I did give some guest lecture to electrical engineering students or electronic engineering students. They are making small robot. Okay, so then when they're doing small robot, the intelligent robot going to navigate in some maze or some, autonomous car, all right? So what they do is they have loads of sensor data coming. Is there's a wall in front of us, there's a corner, I need to turn. So the sensor data coming in as a stream, as a signal, okay? So it's basically like X. So based on the X value, they're going to decide, am I going to turn right? I'm going to turn left, this robot, okay? So the problem is those sensor data will come with noise. Suddenly, there's not going to be clean. Suddenly, there will be certain spark of, oh, there's very close wall, but actually they are false signal. So a simple moving average filter will improve the sensing process massively. So it's very useful, although it's very simple. What do they do is they, rather than directly take into those signals, they make a small average filter. So this is moving average filter. So they make decision based on a filtered signal, which is YN. So in that case, any kind of substantial a sudden change of the signal will be slightly smoothed out. So it will make sure it is real world in front of us, so the car going to turn over or something like that. So this is simple, just very simple example. So the equation representing moving average filter is fairly simple way. So you just say yn equal to xn plus xn plus 1 divided by 2. Or yn equal to xn minus 1 plus x divided by 2. So the two value, which is a neighbor value, and then you calculate output based on the average of these two values. So every two values, they calculate the average. So the concept of that is then your output will going to be like this, 2699620. Okay. So in terms of audio processing, this actually results in some sort of a low pass behavior. One additional thing I'm going to talk about is this expression xn minus 1, those kind of expression. And actually this xn plus 1 means the future sample, and xn minus 1, which means the previous sample in comparing with the current sample xn. So normally the current value is n, and n minus 1 is the past value, n plus 1 is a future value. The next example is a recursive filter, is IR filter. So far, we're talking about the filter is the value is calculated, the output value y is calculated by the input values using input values. So in this case here, the output value y is calculated by both input value and the previous output value. Okay, so you can't calculate from the input value and the current input value, because current output value, because it doesn't exist yet, but the previous output value can be recorded. So in this case, we call it a recursive filter. And this is a different type of filter which doesn't normally exist in sort of natural way, like a convolution. So we call it FIR filter. Why it is IR filter? IR filter stands for infinite impulse response, because you're taking the output and feed back to the system. So in that way, it really can result in if you only input an impulse into the system, it might result in infinite impulse output. Okay, so that in that case, so it can be infinite impulse. Okay, so let's looking at this equation. So this equation basically says the output signal current yn is going to be equal to xn plus yn minus 1. So that means the y value, which is previously output. So when the system has previous output, then it can calculate the average between the previous output and the current input. And so this is average. So divided by 2 is average. The problem of that is sometimes is they say, if you don't have, how about the first value? So when we start this system, you wouldn't have any previous output values. So in that case, we're normally using zeros instead of previous values if it doesn't exist. Okay, so here summarize the syntax we use to actually construct the filter structure. And there are also some important concept we need to apply in the practice. Xn representing the current input value. So n minus 1 means past input samples. So you can have n minus 2, which is past 2. The two sample period ago, the sample. And x plus 1 is future input samples. So in a reality, in practical, we couldn't use, in mathematical form, you can do that because we can say all the signal is offline. We can look at the signal and say, hey, this point, if you take this point as current, then we can have future and past. But in the real-time processing, in the real-time implementation of filter, we normally don't use that because we cannot predict future. All right, so it doesn't exist. So that's why I say if it is non-causal filter. So non-causal filter means offline filter. Yn current output sample, Yn minus 1 past output sample, Yn plus 1 is future output sample. Again, it cannot be used. I think not even it's in non-causal filter. All right. So in our case, we are not going to use this one. I'm not going to use that one. So in the equation we're going to express will be real-time causal filter. There is cause, there's consequence, a causal filter. There we don't predict future. Okay, so here is the causal system. So the causal system basically means the current output Yn only depends on the current and the past input sample and or past output signals. So that's very easy to understand. Okay, we're only dealing with causal signal because it can be used in real time. Actually, real time application is very, very important for audio, you know. So I think most of DAW now need to support real time processing. Okay, so one more word. So mathematically, certainly you can design your system as non-causal. All right, non-causal. So you can look at the signal offline and talk about, but then can convert causal system by time shift or delay or buffer. So this is really, I mean, it sounds like a very fancy process, but it's actually indeed very simple. Okay, so think about if you're going to design your system. You say, okay, I'm going to remove this noise using this filter, but I need to looking at like 2 seconds of the samples, 2 seconds of the audio. Then you can think, oh, maybe we can convert that to in sort of real time, but I at least need to buffer 2 seconds because my filter relies on 2 seconds of audio. So then you can think about if that's realistic. For example, if I'm going to use this in whatever Ableton Live or PD, Max MSP you guys are using, it's not feasible because you have to wait 2 seconds to actually have output. So it's not implementable. But if the system you only need like a 2 millisecond or 20 millisecond of buffer of the sample to be able to implement filter, yes, you can. Basically, you just say this channel will delay 20 milliseconds, or the whole system will time align with that. So that kind of in practice, we're not going to talk about too much now. All right. Okay, so, and in previous example, I also showed 2 types of filter. One is called FIR filter, stands for finite impulse response filter, and the second one is infinite impulse response filter, IR filter. Okay, so this is quite a popular term. If you're going to search Google about digital filter, they always show these 2 categories. These 2 categories has structure difference. So for FIR filter, summarize, the output signals are calculated from and only from input signals. There's no feedback in the loop in the structure. So that's why it's called non-recursive filter. Whereas IR filter, the output signal are calculated from both input and the previous output signal. So you have to buffer the previous output signal. There is feedback loop because output is going to be feedbacked in the system, buffered, and to be able to use it for calculate next output. So the filter is called recursive filter. For IR filter, well, there are some advantage of both filters. So FIR, straightforward to implement. There's no problem for we call instability because there's no recursive filter. You don't get this positive feedback. I mean, in music sense, everybody probably experience this positive feedback problem. Is that proper terminology? Maybe. I mean, I don't know. So when you have a microphone speaker set up, your say something like when you're doing this conference, if some people open their speaker and their microphone, so my voice getting into the system and amplify again and again, and regarded this very sharp noise. This is positive feedback. So FIR doesn't have this because they have no feedback in the system. Whereas IR, it would happen. So if you not design properly, you'll end up with amplify certain frequency, and up to the maximum and clipping. So that's kind of unstable design of IR filter, which we want to avoid. But the advantage of IR filter is normally it takes less complicated structure to implement a certain filter because it can use output information. But in practical, we will see more. Okay, so now we come back to the theoretical construction of expression filters. The couple of equation we demonstrate here is previously basically can be summarized as these two. So remember we did this, sorry, come back. So we got exact number here, 2. So this equation actually can be write as this. For example, I can write as yn equal to, so this equation can be rewrite as 1/2 multiplied by xn, then plus, and 1/2 multiplied by y n minus 1. This equation can be rewrite into that. And this is already, we know it's average filter. So this 0.5 or 1/2 half is the coefficients of these two terms. Okay, so to look at this, we can actually understand the general form of expression. So we have coefficient with the input signal, previous input signal, and there's two previous signals. So okay, so this representing a typical FIR filter. This FIR filter has 3 coefficients: B0, B1, and B2. So if the filter has been designed already, so that means you know the value of B0, B1, B2. In previous MATLAB exercise, what we did is basically using different like SP2 or filter design to actually obtain those coefficients. Okay, so those constants appear in this expression are called filter coefficients, and the order of this filter is the largest number of previous input. So in this case, the order of this filter is 2, because with the largest number of previous input is 2. So we maximum need to buffer 2 previous input signals. This is current. Well, current means like the current system sampled from the microphone at that moment, but those are the previous signals. Okay, so the second equation demonstrates the expression of one example of RIR filter, infinite impulse response filter. Okay, so this expression says yn equal to not just the xn, which is input sample, and xn minus 1, which is previous input sample, but also the previous output samples. So the output sample also participate in this process. However, we're using a different coefficient, normally using different symbol to represent the coefficients which applies to previous output sample A. So we're using B representing the coefficient of input sample. We're using A and representing the coefficient of output samples. So normally we call it B0, B1, B2, A0, A1, A2, and so on. It's a bunch of coefficients, not just one. And this again is very simple filter. The order of this second filter is 1 because we're only using 1 previous samples. People would ask whether we consider of the previous input or previous output to decide the order. So the order will be the maximum previous sample, either depending on which one is, is larger, which number is larger. So we use that as the order of the filter. Okay, so we're going to now looking at very, very simple filter to start with. So the first very, very simple filter is a simple gain, just or amplification or attenuator. So the expression of that filter basically is yn equal to k xn. So k is your coefficient. So depending on the coefficients, you can either create an amplifier, or if k is between values 0 and 1, it will become attenuator. The second simple filter is we call a moving average filter, and we've done that in previous slide. It's just basically writing in the different form. So this is a simple type of low pass filter, and it tends to smooth out the high frequency variation in the signal. The third filter we're looking at is the delay filter. So pure delay filter. So we can say we have input signal, we have output signal yn, which is equals to a previous input signal xm minus 1. So to understand that, basically is say y0 equal to x minus 1, y1 equal to x0, and y2 equal to x1, just equal to 1 delay samples. So if the input, this input signal is current, if we don't have any previous input sample, we just take it as 0. Okay, so that looks like a digital filter can be understood in very, very simple way. However, now we're going to looking at how can we judge those filters in terms of their frequency behavior, and how we're going to do that. So if you Google search the digital filter, this is what I did. Okay, Google search digital filter and show a Google image as our result. You will say in the first page of the result of the search engine, you will probably end up with all this type of thing. So the digital filter can be expressed a different way. So normally it can be actually expressed as a kind of called structure diagram, which or signal flow diagram. So those diagram is very good in the early days to implement digital filter in hardware form. Without computer being very powerful, we can actually implement those filters in a very, very simple way, a simple hardware form. The simple hardware would only have this delay buffer, one buffer delay, and delay lines, and a signal root. I think for you guys, maybe those diagram is not hard to understand, because what audio engineer does normally is always looking at the signal flow. Okay, so then, for example, in this case, the signal xn coming, then this is output yn coming out. So signal coming and going to delay and apply the coefficients, and the signal yn going to delay line, those square with z minus 1 are delays, and apply the coefficients of output signal and synthesize to a new output signal, such as that. So you can also say there are some equation involved this z, kind of a very strange symbol called z. This is going to be, I think, most complicated concept in digital filter from my experience with some of my students is to understand this z. Let's have a look the generic form of expression digital filters. So there are different way express digital filter. The way we so far talking about is called difference equation. This is a difference equation which using a very straightforward symbol x and y and to represent previous signals. However, this equation doesn't give us any insight of what type of filter is that. So it might, what is this low pass, is high pass? We don't know. So that's why we need to have different way to looking at this filter to be able to mathematically tells us whether this filter is low pass or high pass, the spectrum property of that. So then we're going to introduce a concept of called Z transform. I mean, I have to say, my slides of Z transform are very engineering approach. It's not mathematical at all. Okay, so I used to give lecture to other group students because there are loads of mathematical rigorous and to discuss about this Z transform in being kind of different domain, how you looking at this convergence in Zoom, stuff like that, which we ignored. And you can certainly read other textbook about that. But I think the concept I'm going to teach here is sufficient to understand the basic idea and from programming point of view. Okay, so Z transform. So Z transform, why we need Z transform is because from difference equation we just look at so far here doesn't give you any facility or fundamental tool to be able to explore the frequency domain property of that. So then we need to using a transfer function, which may be able to actually just getting relationship between input and output, ignore all the previous terms. So with the transfer function, the filter can actually be analyzed in terms of the characteristic, such as the frequency response. So how we going to convert difference equation to Z transform form is not very difficult. But by doing that, you'll be able to understand loads of textbook and help file in MATLAB because most of them are express filter in the Z transform format. So, okay, let's just have a look at this process. The process is fairly simple. So first of all, we introduce, we call a unit delay operator, unit delay operator. The unit delay operator is denoted by a symbol of Z power minus 1. Z power minus 1 is the unit delay operator. Why it is Z power minus 1, I don't know. There's certainly a mathematical rigorous back behind that. We can, at the moment just skip that because we will establish a simple relationship between a difference equation expression, which is here, and then the delay unit expression, which is on left side. So what basically shows here is if you have any kind of a delayed version of input signal xn minus 1, it's basically equivalent to the current input multiplied by a delay factor z power minus 1. And that delay is delay one sample. So the delay, the number of samples delayed, for example, minus 1, becomes the exponent of this delay factor, z power minus 1. So in that case, we actually encode time into this delay factor z. All right, so because the difference between xn and xn minus 1 is the time. So this is current input and this is previous input. So we actually encode this time into z power minus 1. Okay, so to understand that, we can use some example. For example, we have a series of input signal, 5, -2, 0, 7, 10, etc. So we basically encode that. If we say z power minus 1 multiplied by x1, which is x0. So it's no longer representing the current input, whereas it's representing the input before this one. So this is the example showing what happens when we apply z power minus 1. So the same rule applies to output samples. We encode the time difference into the factor of z. So the quantity, the number of delay in terms of time will convert into the exponent of z factor. So for example, if you delay 2 samples, xn minus 2, it will become the exponent here. It refers to delay 2 sample. So what is significance encoding time into certain mathematical form is because philosophically, frequency and time has very important relationship. All right. So I think in one of the lecture, I used to say, give you 1 sample. Do you know what frequency of that sample? You don't know, because it's just 1 sample. Give you 2 sample, do you know the frequency of these 2 sample? You probably still don't know. So whatever FFT or digital filter, you have to have a bunch of samples which appear in the time axis, appear in the time domain. So think about the time, and when the sample appear in the certain pattern, all right, repeat itself in the certain pattern, that will give you frequency information. The frequency is really how often the sample appeared in certain pattern. So time is important. By doing this, we actually encode time in the equation. So we can looking at the frequency response, stuff like that. I mean, probably this kind of philosophical thinking, try to give you some intuitive understanding of that. Then in practical way, mathematical way, we then can convert this general form of a digital filter in difference equation. Okay, so you can say we have a general yn minus 1, yn minus 2, and a general form of xn minus 1, xn minus 2. So it can be IR, well, it looks like an IR filter, but it also can be converted into FIR filter if A1, A2 are equal to 0. So something minus multiplied by 0 is also 0. So you only got opt here. Okay, so it can be FIR or IR in terms of the mathematical equality. So that one can using their transform. So if we can using their transform, so we convert all the previous output samples, this is previous output samples, become encoding the past time into Z factor, just left the current output sample with multiplication of the time factor, and encoding all the input sample with current input sample multiplied by the time factor. So in that case, what we got is very interesting result, because in that case, we eliminate all previous one, because all this previous sample has been encoded into that stuff. So we end up with this equation. So we convert everything become relation with current output sample and the current input sample. So in that case, we can actually collect from using mathematical some sort of analysis algebra, I think some sort of algebra, you can actually collect the term, common term, which is yn or xn outside of the bracket. So you only left some coefficients as well as this delay factor in this bracket. So we rearrange this equation, we were getting this final form of transfer function. Okay, so this final form of transfer function actually tells us a very important information that basically says we can express a digital filter with a structure as a current output yn with a current input xn. So basically transfer from input signal to the output signal can be expressed by the right side of this equation, and this is called transfer function, because what it does is transfer the current input to a current output. The previous input signal and previous output signal information has been encoded all in Z. So we left some nice expression which has got no input output signal involved, and this is independent to any input output signal. And this independency is characteristic of any digital filter. So in this case, what we can say is the digital filter can be decided by a kind of expression which takes in form of the fraction, which is numerator. This is numerator part, and the denominator part. So the numerator is in terms of b0 plus b1 z power minus 1 plus b2 z power, and so on. You can have more terms. And the new denominator takes shape with the coefficient a0, a1, a2. So those are coefficients going to apply to previous output samples. And those coefficients are going to apply to current and previous input samples. So those are the digital filter form. Okay, so from there, we can actually derive filter properties, which I'm going to, actually I put 2 slides here because condense the teaching here. So just bear me a second. I'm just quickly show you, because that's going to be more mathematical form, which is less useful for our engineering students. So I'm going to quickly show, but you can have a look at that slide. A few slides on this is just a reminder, because normally I take these 2 lectures, but I don't think the second part is vastly important, but it's important to understand it. All right, so okay, so what is this Z indeed? How can we, from Z transform, we can judge this filter is low pass or high pass, is most people concerned about, is because mathematically Z is not equal to frequency, but it has frequency information encoded there. So mathematically, Z is equal to, I have this exp j omega t here. Basically, Z is original expression is equal to exp, means e to the power of some, e to the power of j omega and t. And omega is your frequency. Omega is angular frequency, which is equal to 2 pi f. So f is your frequency. So in this case, Z is linked with the frequency. So if you're going to rewrite that again, so equal to E, the logarithm is kind of like a magic number, like a pi, which is some terms of natural number. J is imaginary part. Omega is 2 pi f. And T here is your sampling period, which is 1 over Fs. So this is what actually Z is. I mean, it's probably super complicated, however, but you probably know the frequency information is actually encoded in Z. So to be able to judge if this expression, what kind of frequency response property of that expression, we need to substitute Z with this expression. And then we can actually calculate the magnitude response and the phase response of that digital filter. Okay, so well, this basically just showing we substitute Z with e to the j omega t. And you now, I mean, I couldn't understand it. It's very abstract, but you have to accept it. Basically, what basically says is the frequency is in the exponent as well as its imaginary number, because it's multiplied by j. J is imaginary number. Actually, if you look at Euler's entity, this e to the j omega t can be rewrite as kind of sine and cosine plus together. All right, so you can write this as, I think it's like cosine j omega t and plus j, which is imaginary part, with a sine j omega t. Sorry, the j is probably right wrongly. So j should be, sorry about writing the mouse. So that actually contains both sinusoid waveform components. In that way, intuitively, we want to understand that. Okay, so to calculate the magnitude response, there's a formula with that. We not require people to do that. It's just like a knowledge for people to know. So the amplitude response, which is magnitude response, similar, is basically saying we need to calculate absolutely number of that. By doing absolutely number, the result will eliminate the imaginary part, because you all know when we calculate a complex number, absolute value of complex number, you are actually calculating the distance between the complex number to 0. Okay, so if you have the imaginary x and the real x. So by doing that, we eliminate all this imaginary. We end up with expression of coefficients and the frequency. And we can calculate the phase response by calculating the phase of this complex expression. So at the end of the day, the digital filter mathematical expression is a complex form. If you want to find amplitude response, you calculate absolute number of that. I think I got expanded version of this. So for example, you just need to find the real part of that expression, square, and find the Im part. This is equation. So here basically it says the real part of the expression. This is your Z transform, which replaces Z with e to the j omega t. Square of that, and imaginary part, again, this is I am representing finding imaginary part of that, and the square of that, and square root. So giving any f, for example, omega can be 0 hertz or 1 hertz, 2 hertz, they will give you certain value, maybe 0.8 or 1. And in that case, you basically, with that result, with this equation, so giving any f frequency, then you can draw any kind of magnitude response. So it will showing as this is low pass or high pass and so on. So that's why we leave it very late to actually say, because the mathematical formula to calculate whether this, or to be able to representing this in a low pass or high pass form is fairly complicated. But again, I don't think it's necessary, because in the next lecture after Easter, we were talking about some the internal details of, because nowadays people design filter using software package, all right? So we actually come backwards. I want a low pass filter, so we be able to calculate the expression, and backwards what are coefficients. So the next session after Easter, what I'm going to talk about is those internal structure, how we calculate the filter of that. I think I've got quite a few slides here, but I think then after Easter, I'm going to go through some of them anyway. So that part is going to be just knowledge point. We're not going to be assessed on that anyway. All right, so I think the time is up now. It's already 11. So any questions do you want to ask, or we can chat over the Zoom if you want?